Welcome to today's paper reading. Today's paper is titled, Chinchilla Scaling, a Replication Attempt. This paper was published on the AR14 preprint by Tamay Besiroglu and colleagues from Epic AI. In this abstract, the authors attempt to replicate Hoffmann et al.'s third estimation procedure, which involves fitting a parametric loss function to data reconstructed from their plots. They find that the reported estimates are inconsistent with the first two methods, fail to fit the extracted data accurately, and report confidence intervals that are implausibly narrow, requiring over 600,000 experiments. Two factors contribute to these findings. The optimizer stopped before convergence due to a poor choice of loss scale, and the parameter estimates were rounded in a way that introduced substantial bias. In contrast, the author's rederivation of the scaling law using the third approach yields results that are compatible with the findings from the first two estimation procedures. Hoffmann et al., 2022, explored the optimal model size and number of training tokens for transformer language models within a given compute budget. They trained over 400 models, ranging from 70 million to over 16 billion parameters, using 5 billion to 500 billion tokens. Their key finding was that for compute-optimal training, model size and the number of training tokens should scale at equal rates. This led to the development of the Chinchilla model, which adheres to these scaling laws. The authors employed three methods to estimate the compute-optimal frontier: training fixed-size models on varying tokens, training varying-size models with fixed compute budgets, and fitting a parametric model of loss as a function of model size and training tokens. This research has been replicated by Erdil et al., 2023, and by et al., 2024, who also found proportional scaling but noted sensitivity to data quality. The parametric form of these scaling laws has attracted independent scientific interest, influencing theoretical explanations of neural scaling laws and optimizing compute expenditure. In this section, the authors reconstruct the data from Hoffmann et al.'s Figure 4. They first downloaded the PDF from Hoffmann et al.'s AR14 submission and converted it to SVG format to accurately determine the y-coordinates corresponding to specific model sizes. The authors assumed that the text labels indicating model sizes were vertically centered on their respective y-axis values. However, they encountered precision issues due to the color scale being limited to 256 hex values, which restricts the accuracy of loss value estimation to approximately 0.01. Additionally, a few data points stand out, particularly a column of points with training flop around 10 to the power of 19 where larger models obtained high loss values, up to 70% higher than models with similar compute budgets. These outliers correspond to the lowest ratio of training tokens to parameters, and their inclusion does not materially change the conclusions about the poor fit of Hoffmann et al.'s estimated scaling law. The authors replicated Hoffmann et al.'s parametric scaling law, which is defined as L, N, D, equals E plus A slash N caret alpha plus B slash D caret beta, where N is the number of parameters and D is the number of training tokens. To fit this function, they minimized the Huber loss. Their estimated model was L, N, D, equals 1.8172 plus 482.01 slash N caret 0.3478 plus 2085.43 slash D caret 0.3658, compared to Hoffmann et al.'s model, which was L, N, D, equals 1.6934 plus 406.4 slash N caret 0.3392 plus 410.7 slash D caret 0.2849. The authors found that the values reported in Hoffmann et al.'s text source were more precise. They conducted a Chi2 test to assess the significance of the differences between their estimates and Hoffmann et al.'s estimates, finding a p-value of less than 10 to the power of negative 51 when excluding outliers. Parameters E and beta showed highly significant differences, with p-values of 2.6 times 10 to the power of negative 6 and 1.1 times 10 to the power of negative 4. Respectively. A likelihood ratio test further confirmed that their model fit the data better, with a p-value of less than 10 to the power of negative 235. Figure 1 presents the display contour extracted from the left subfigure in Figure 4, which has been reproduced in this paper. This detail highlights a specific aspect of the original figure, providing a clearer view of the contour's characteristics and features. Figure 2 presents our reconstruction of the data originally depicted in Figure 4. This reconstruction serves as a comparison to the original data, highlighting the accuracy and fidelity of our method. The key aspects to observe include the alignment of the reconstructed data points with the original, as well as any discrepancies that may indicate areas for further refinement in our reconstruction techniques. Table 1 presents our parameter estimates along with their standard errors, which are derived through bootstrapping. The table includes estimates for parameters A, B, E, alpha, and beta, and compares these with the estimates provided by Hoffmann et al. The standard errors are indicated in parentheses, reflecting the variability in the estimates. This comparison highlights the differences between our methodology and that of Hoffmann et al., providing a basis for further statistical analysis and validation of our findings. Figure 3 presents a plot of the residuals from Hoffmann et al.'s estimated model using rounded parameter values, compared to our estimated model. The residuals for our model are tightly concentrated around 0, indicating a significantly better fit. Specifically, 98% of our Huber loss values are smaller than the median loss value of Hoffmann et al., and our model achieves lower losses for 90% of all observations. This comparison highlights the superior performance of our model in fitting the data. Table 2 presents the log likelihood values for the parameters proposed by Hoffmann et al. And our best fit parameters, calculated on our dataset while excluding 5 outliers. By assuming the unrounded parameters from Hoffmann et al. As the null hypothesis, we conducted a likelihood ratio test to demonstrate that the difference in log likelihoods remains highly significant. This table is crucial for understanding the statistical significance of the parameter fits and the implications for the model's performance. Figure 4 illustrates the residuals of the estimated models by Hoffmann et al. And our own. The residuals for our estimated model are tightly concentrated around 0, indicating a better fit to the data. In contrast, Hoffmann et al.'s model, when using the rounded parameter values reported in their paper, shows a poor fit to the data. However, when using the more precise, unrounded parameter values from their text source, there is a substantial improvement in the goodness of fit, although it still does not match the performance of our model. This figure highlights the importance of precise parameter estimation and the impact of rounding on model accuracy. Figure 5 illustrates the optimal ratio of training tokens to model parameters based on our estimates, with shaded regions indicating 80% confidence intervals. Our estimates align with the scaling policy used for the Chinchilla model, but contrast with the parametric model estimates provided by Hoffmann et al. This discrepancy highlights the need for robust and reproducible parameter estimates in scaling law research. The authors identify 3 main issues with Hoffmann et al.'s estimates of the Chinchilla scaling law. Firstly, the estimated model fits the reconstructed data poorly, primarily due to rounding of parameters. Secondly, the confidence intervals are too tight given the number of data points, requiring many more observations than available. Thirdly, the estimated model's scaling policy is inconsistent with other approaches. These issues arise from a problem with the optimizer, which halted before convergence. This highlights the need for running the optimizer to convergence for accurate estimates. Hoffmann et al.'s paper has had a significant impact on the language modeling community, influencing models like Google's Gemini suite. Therefore, robust and reproducible parameter estimates are crucial. The authors also emphasize the need for precision in reporting scaling law exponents, given the large numbers of parameters and tokens involved. Finally, the work underscores the uncertainty about compute optimal scaling, suggesting that tighter estimates could save significant compute resources. In this appendix, we address the robustness of our findings by including the 5 outliers previously excluded. Despite the increased uncertainty in parameter estimates, our main conclusions remain consistent. The model's significance is evident with a chi2 p-value of 6 × 10⁻50, indicating substantial deviations in parameter estimates. Specifically, parameters E and beta show significant differences from their expected values, with p-values of 2.0 × 10⁻5 and 2.4 × 10⁻3, respectively. Additionally, our analysis supports an optimal scaling of 25.6 tokens per parameter. We further validate our approach with a likelihood ratio test, converting the Huber loss minimization into a likelihood maximization problem. This test compares unconstrained fits with those where sigma is allowed to vary, using a chi2 distribution with 5 degrees of freedom to assess the difference in log likelihoods. Table 3 presents our parameter estimates along with their standard errors, which are derived through bootstrapping. The table includes estimates for parameters A, B, E, alpha, beta, and A, with their respective standard errors shown in parentheses. Additionally, our estimates are compared with those from Hoffmann et al., providing a comprehensive view of the differences and similarities in the parameter estimation methods. Thank you for watching.